Hello, everyone. Welcome to today's lecture in quantum computing. As you can see, I'm still recording this from home. In California, the lockdown situation is still the same, so you can't go out. I hope you don't mind the environment. I'll try my best. Today, we will learn about three interesting things that are three algorithms that will show the power of quantum computing, or things that you can do with a quantum computer that you can't do classically. The first one is super dense coding, which I wouldn't precisely call an algorithm, but it shows that you can transmit 2 bits of information with just 1 bit in quantum computing. Then we will look at quantum teleportation. And I know teleportation sounds exciting, but what it is just a particle statistical thing. And the third thing we will look into today is Deutsch's algorithm. So Deutsch's algorithm is one of the algorithms, or actually the first algorithm, that showed that quantum computers can do things that classical computers cannot do. So that we have a speed up in processing. All right, let's start with super dense coding. Do you remember in the beginning of the lecture, or the very beginning, we talked about entangled states. So for both super dense coding and teleportation, we will start with an entangled state that is shared between 2 parties, Alice and Bob. And just to recap, I'll show you how to create an entangled state between 2 qubits and how we use it for super dense coding and teleportation. So we have 2 parties, Alice and Bob. Let's call them Alice and Bob. And you have an EPR source. EPR stands for Einstein, Podolsky, Rosen. And this is just because these 3 physicists came up with these entangled states and description of these entangled states. There's something else in physics. It's called EPR bridge, Einstein, Podolsky, Rosen bridge. You may know that from Star Trek. It's a wormhole. Anyway, so we have this EPR source, and the EPR source generates an entangled state, which is shared between our 2 parties, Alice and Bob. And let's just recap how we create an entangled state. So remember, we have, if it's just 2 qubits, there are more complex entangled states, of course. If we have 2 qubits, we just write them down in our initial registers. So then we take the first qubit and we apply a Hadamard transformation to the first one, which lifts that first one into an equally weighted superposition. We apply a controlled NOT operation here, and that will give us the state right? So how we get to that, if we just have a look, remember, you can also write it down that way, or you can write it down that way. So if we take this first one, so the Hadamard transformation applied to the first qubit, that's going to result in, this state, but then we still have our second qubit here, right? And our second qubit here, that one is still in the state 0, definite state. So we multiply that in, we execute that, which results in all right. And then we still have the controlled NOT operation that we apply. And you remember the controlled NOT operation, what it does is it takes the first qubit as an input bit, as a control bit, and checks if that is 1 or not. If it is 1, it applies a NOT transformation to the second one. So the controlled NOT, let's be correct here and write controlled NOT, C NOT on that state, which results in which is an entangled state. It's an entangled state because that very state here cannot be decomposed into a tensor product of single qubit states. So therefore, it cannot be created out of a tensor product. Okay, this is our starting point. When we say we share bits between Alice and Bob, then what this means is, for that state, the first half of the qubits of the 2-qubit state belongs to Alice. Right? This and this is Alice. So Alice has a 0-1 superposition. And the second one belongs to Bob. Same for him. Okay? Now, what we can do with superdense coding is we can use an entangled quantum state of 2 qubits to double the classical capacity of the quantum channel. And this is because entanglement can change 1 qubit into 2 qubits, okay, in that case. So we simply stick with that state here. And so remember, if 2 qubits are entangled, if I do something to 1 qubit, it affects the state of the other qubit too. Then you remember, so one thing is used here, you remember the Pauli transformations, right? The Pauli matrices. If we quickly write that down again, so we have 3 of these plus identity. So we have our NOT transformation here. We have our Y, which is that one here. We have our Z. And we have identity. Okay, so we have these 4 transformations. We always need identity when we don't want to do something to a qubit state. So if we have a 2-qubit operation, so that correctly would have been written down as apply Hadamard to the first one and identity to the second one to this state, right? So we have Hadamard here, we have identity applied to that state. So it's a 2-qubit transformation. But only do the Hadamard to the first one and leave the second one alone. Anytime I leave a qubit alone, then I have to apply identity to that qubit. So if we, in that example, want to send some information, or if Alice wants to send some information, then it's easy to check. So we can just verify based on these 4 transformations that we have, what would happen to the 2-qubit state if Alice applied one of these 4 plus identity to the second to this 2-qubit state. So one of these 4 to her half of the qubit, and identity, always identity, because she cannot apply anything to the second half of the qubit. It's Bob's, and it may be physically separated, but still she can apply that state, that transformation to each of the qubits. And let's give that a quick try. Let me make some space here. So what Alice can do, that's how it starts. Let's look at the first combination of transformations. So she can apply I to the state that we just had before. Let's call our state. Let's quickly write it down here again. Let's call our state psi. So let's apply the transformation I to the state psi. What's the result? The result is the same, of course. Yeah. Let's do the second one. So what if Alice applies X and I to that state? So if we do that, again, it's only Alice half that is concerned by the transformation. So the result will be the first half here becomes 1, second one remains 0, plus 0, 1. Okay, then let's look at what happens if we apply the y. So we do y times I applied to our state psi here, which results in 1/2 minus 1, 0 plus 0, 1. And let's have a closer look at how that comes about. If you let's try the matrix calculation. So let's say we have our y transformation here, and we have 0, 1, minus 1, 0, and we applied it. So we only have 0 and 1 here. So we applied it to the state 0, which is 1, 0. Then we see 0 times 1 plus 1 times 0 is 0, and we have minus 1 times 1 plus 0 times 0 gives us minus 1. So that means 0 becomes minus 1. And we apply it to the state 1, which is 0 times 0 plus 1 times 1. We have minus 1 times 0, 0 times 1. That means 1 becomes 0. And you see what happened here. So if we look at that first, so 0 becomes minus 1. That means that one here becomes minus 1, which becomes minus 1, 0 then, because that one remains. And the state 1 becomes 0, which then gives us this result here, okay? And then let's do the same for the last transformation for z. If we apply z I to that state, the result is, let's do the calculation again, just as an exercise here. So we have 1, 0, 0 minus 1, which is almost identical to the identity transformation, except that minus sign here. And so if we apply that to our state 0, the result is 1 times 1 plus 0 times 0, 0 times 1 plus minus 1 times 0 remains 0. But then if we apply it to state 1, one times 0 plus 0 times 1, 0 times 0 plus minus 1 times 1. That means, so this one here remains 0, that remains 1, but it becomes minus 1. For our state up here, it means, if we have a closer look, 0 remains 0, therefore we remain in that state. 1 becomes minus 1, which results in this state. All right. So it's not done yet. Everything we just saw, everything that happened up here, this is our original state, everything that happened up here was done by Alice. Now it's Bob's turn. Bob now has a look at these states, and he applies a couple of things. So the first thing he does is apply a controlled NOT operation to that state. Let's say this is Bob's action plane here. So a controlled NOT operation, let's give these states names. Let's call that one here psi 0. We call that one here psi 1, we call that one here psi 2, and we call that one here psi 3. So let's take psi 0 first. If Bob now applies a controlled NOT operation and controlled NOT operation to the state psi 0, then the result will be um, 0, 0 plus 1, 0. For the controlled NOT operation on state psi 1, we see the 1 here, so therefore this becomes 1, 1 plus 0, 1. For the third one, if we apply controlled NOT to psi 3, the result will be minus 1, 1 plus 0, 1. And for the last one, we apply again our controlled NOT operation. Okay, this is psi 2, sorry. We apply it to psi 3 here. Psi 3 becomes 0, 0 minus 1, 0. We're still not done yet. So Bob, now after applying the controlled NOT operation to this state, does the following. He separates out, so which means we just write our states in the following form. So you can see here the second qubit. So Bob's qubit is 0, here it is 1, here it is 1, 1, here it is 0, 0. So what we can do is, or what Bob can do is, let's just write it in a different way. He can write that very first state as 0 plus 1, 0. Second one as 1 plus 0. That's 1. Third one here minus 1 plus 0. 1. And the last one here becomes 0 minus 1, 0. All right, so we have these 4 states, and these are the 4 states we're going to continue to finalize the experiment. I will erase this now, we don't need that anymore. Continue up here. So what we do next is we take, so what Bob does next is actually he applies a Hadamard transformation to this first bit here. And if you look at that, you remember the Hadamard transformation applied to the state 0 gives you 0 plus 1 with a positive relative phase. If you apply the Hadamard, same here, if you apply the Hadamard transformation to the state 1, it gives you 0 minus 1 with a negative phase at 1. Same here. So these two are identical, okay? Let's look at the final result. So Bob does the following. He takes Hadamard transformation and leaves the second qubit alone. And the Hadamard transformation, you know, as everything in quantum computing is reversible, it takes a superposition state and collapses that into a definite state again. So the Hadamard transformation applied to psi 0 gives us 0 0. The Hadamard transformation applied to psi1 here, and identity psi1 gives us 0, 1. 0, 1. The Hadamard transformation applied to psi2 gives us 1, 1. And the Hadamard transformation applied to state psi3 gives us 1, 0. So you see what happened here. We have 4 orthogonal states, definite states. They're not in superposition anymore. It's definite states. For each of these definite states, so each of these definite states can be distinguished when you measure the system. So that means depending on what information or what bit value Alice wants to transmit, you could say this is 0, 1, 2, 3, or 1, 2, 3, 4. Alice chooses her first initial transformation, and the sequence of transformations that Bob applies is always the same. So depending on what Alice did first, she can, with only having access to one bit of information, the one entangled half of her bit, she can apply, she can transmit 2 bits of information, because you need, if you want to represent 4 values, you need 2 bit values to represent them. It's not possible with only 1 bit value. All right, maybe we look at the detail of how the Hadamard transformation in matrix form applied to that first state looks like. So I will again erase these other 3. Then let's look at the Hadamard transformation. So if you remember correctly, then the Hadamard transformation looks like that. We apply that to that superposition state of 0 and 1, which is identical to writing we apply 1 times 1 over the square root of 2 plus 1 times 1 over the square root of 2 gives us 2 over the square root of 2. And then we have 1 times 1 over the square root of 2 minus 1 times 1 over the square root of 2 gives us 0. And then we shall not forget that we still have our 1 over the square root of 2 here. If we multiply that out, then the result is 2 half, which is or equals 1, 0. So you see the superposition state of 0 plus 1 here again becomes 1, 0, which is 0. Yeah, that's it. That's super dense coding. So remember the 4 states that we get as a result. They are orthogonal to each other, which is one of the requirements that we have. So now one might worry why, or that this isn't so strange at all, because when we send a qubit from Alice to Bob, why can't we just send an infinite amount of classical information in the alpha and beta amplitudes of our qubit alpha 0 plus beta 1? The reason for that is, and philosophically, is that the amplitudes of a qubit are more like probabilities than they are like real properties of our system. So you may as well ask the question why sending a probabilistic bit doesn't allow one to send an infinite amount of classical information in the probability P, or however you want to call it. So more concretely, there is a theorem that I encourage you to look up. It's called Holevos theorem, which says basically in a very precise way that a qubit can only be used to send a single bit of classical information when there is no extra entanglement around. Okay, there is more information about that in my slides, so you may also go through that. But for superdense coding, that's it. The next thing we're going to look at is teleportation. All right, Now, after super dense coding, we want to take some time and talk about teleportation. I just want to write that down because it always feels nice to write down teleportation and have some Star Trek-like thoughts. However, it is not that mysterious. So anytime we talk about teleportation in quantum computing, it's not the teleportation you may know of. You may know it from Star Trek. It's a particle statistical thing. What it means is that we again have two parties. Let's call them Alice and Bob. And Alice is in possession of a superposition state. So that superposition state has some amplitudes, but she doesn't know about the amplitudes. The only thing that she knows is she wants to take her state and transmit that state, that very same state, to Bob. And there are some challenges associated with that. So again, let's start with that assumption that Alice is in possession of a superposition state, and let's call that state phi. Okay, and that state phi comes with some amplitudes, alpha and beta, and Alice doesn't know anything about alpha and beta, but she wants to transmit that state. So one way to do it for Alice would be she just takes that qubit in her lab and puts it in a bag and carries it over to where Bob is right now, maybe at home, and then hand over that state to Bob. However, that comes with some challenges. So at the beginning of this lecture, we talk about one of the reasons why it's so difficult to build up a quantum computer is because it's so difficult to isolate it from its own irrelevant properties and from the environment. And that's one of the problems. So taking that qubit state and putting it in a bag, for the lack of a better metaphor, is very difficult. In that case, it may interact with the environment, it may interact with the bag, which is also the environment. So it will collapse at some point and it will end up in a purely classical state. And that's not what we want. We want to have that quantum state over at Bob's house. So another thing you could do, or Alice could do, is just pick up the phone and give Bob a call and tell Bob some classical information that would allow him to reconstruct this very same state. However, there is another challenge associated with that. We talked about it in the last lecture, and the problem that we have here is that we cannot clone an arbitrary superposition or a quantum state because of the no cloning theorem. So we proved in our last lecture there is no way to copy a quantum state from into another qubit state. Okay, so it's not possible. It's the no cloning theorem. So the goal for Alice still is to send over some classical information that allows Bob to reconstruct that bit. It's difficult still. So if Alice just performs unitary measurement on her quantum state and some auxiliary bits maybe, this doesn't really do anything to disturb the quantum information. It's just rotated into some new basis. And aha, you may say, just in the last example of superdense coding, we learned about how to use entanglement to influence the state of shared qubits. So if, again, Alice and Bob have a qubit state, an EPR state that they share an EPR bit, so a maximally entangled state, and let's give it the name psi, which is 1 over a square root of 2 so the very familiar 2-qubit state that we had before. So again, we have Alice owning one half of it and Bob owning the second half. And this is what we will use for constructing that teleportation circuit. Because any classical information transfer would violate the no cloning theorem. So it would not be possible, simply said. Let me show you how to construct this. So if we start with this initial state here and this shared state, then what we do is we just create the product out of these two states. So we take alpha 0 and that 0, 0 here, which will result in alpha 0, 0, 0 plus alpha 0, 1, 0, 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. Okay, so we're in that state now. Now, what Alice does next is she applies a couple of transformations to that very state here. And the sequence of transformations, and again, remember, we need to check if they commute is applying Hadamard transformation, identity transformation, identity. Since we have 3 qubits here that she wants to apply the transformation to, but then also does a controlled NOT operation and identity. So if you read that, or how you read that is, you apply this one first and then this one here, okay? So it's directly opposite to how you write it. And we apply it to that very state here. And let's give the state, so let's now, from now on, call this whole state here psi, okay? So we apply that to the very state psi and start with this one. You only see 2 transformations here, but still it's acting on 3 qubits because remember the controlled NOT operation is a 2-qubit operation, and here we have an identity transformation, so therefore we have an operation on 3 qubits. Let's do the first one. If we apply the controlled NOT operation, what happens is that the first 2 qubits here are the ones that we want to have a look at. This one remains the same. Then we have alpha 0, 1, 1 remains the same. Then we have beta 1, 0, 0 does not remain the same. So we look at 1 and 0 here, so this becomes 1, 1, 0. And then we have beta 1, 1, 1, which becomes beta 1, 0, 1. Okay? So we did that. The next thing we're going to do is apply the Hadamard transformation and the 2 identity transformations to that very state. So that means we have to look at each of these separately. Let's do that. Let's start with this first one here. So alpha, I just apply the transformation to that state here. One half. Just leave that away for the moment. 0, 0, 0. That results in one half 0 plus 1 times 0, 0 results in 1, 0, 0. Let's do the very same thing for that one here. Um, 0, 1, 1. Results in All right, let's do the third one. So remember, superposition or Hadamard transformation applied to the state 1 gives us 0, -1 with a negative relative phase. And that we apply to 1, 0. And we have we have 0, 1, 0, -1, 1, 0. And then let's do it with the last one too. 1, 0, 1. Again, we have our transformation here. 1, 0, 1. Will result in, again, a superposition state of a negative relative phase at 1 applied to 0, 1 equals 0, 0, 1 minus 1, 0, 1. Okay. Now that we have that, we may remove everything that we have here. And just write that very new state down here. So let's again call it still psi. So we have 1 over the square root of 2, and we might not forget the 1 over the square root of 2 that we have in front of this one here. So therefore, this just becomes 1/2. And we just summarize everything we have. So for this one here, we have the amplitude alpha. So that means it's alpha 0, 0, 0 plus alpha 1, 0, 0. The next one we want to have a look at is this one here. Still, this has the amplitude alpha. So therefore, we will have plus alpha 0, 1, 1 plus alpha 1, 1, 1. 0, 1, 1 plus alpha 1, 1, 1. And we go on. Here, we have the amplitude beta, which means we have beta 0, 1, 0 minus beta 1, 1, 0. And here we have beta 0, 0, 1 minus beta 1, 0, 1. All right. Then we want to continue. So we want to look at where we find two identical states of the first two qubits. Okay, I want to write that slightly different. So that means we have zero, zero. Then we have our amplitude alpha here times, we want to not forget the 1/2. Let me quickly fix this. I have our 1/2 here. So we have 0, 0 here, 0, 0. And then we have alpha 0. Now we want to look at where else we find 0, 0. We find it here, plus beta 1. We want to have these two out. Next, then we want to look at 1, 0. And see that we have the amplitude alpha for 0 here. Where else do we have 1, 0 here? And the amplitude of -1 minus beta 1 here. And we have these two out. Next one is we look at 0, 1. So we have 0, 1 with the amplitude alpha for 1 and the amplitude beta for 0. So we have these two out. Leaves us with these two here. We have plus 1, 1. Gives us the amplitude alpha for 1 and the amplitude minus beta for 0. Okay, so we end up in that state. And what we can see here that Bob's qubit, Bob's original entangled qubit, is projected to one of these 4 states. And what happens next is that Alice does a measurement. So she measures the first 2 qubits. And depending on what the result of that measurement is, Bob's state is projected, or Bob's qubit is projected to one of the 4 superposition states that we see here. So Alice does a measurement, and let's assume she measures 0, 0. Then Bob's state becomes, if she measures 1, 0, then Bob's state becomes alpha 0 minus beta 1. If she measures 0, 1, then Bob's state becomes alpha 1 plus beta 0. And if she measures 1, 1, Bob's state will become alpha 1 minus beta 0. Okay. And then this can be communicated classically. This is something that Alice can tell Bob. So she tells him what result she obtained. And now that Bob knows about the result, so remember we had our first state. So Alice qubit that she had at the beginning was in the state phi, which was given by alpha 0 plus beta 1. So now there are a couple transformations that need to be applied. So if Bob receives 0, 0, the transformation that he applies to his qubit state is identity and identity. If Bob gets, well, let's say 0, 1, continue with that one here, then Bob applies, no, actually he does just apply identity because it's a single qubit transformation. Then Bob applies not. If Bob gets 1, 0, then the transformation that he applies is Z. And if he gets 1, 1, then the transformation he applies is Y. So in any case, whatever he does here, if he does it correctly, will result in which means Alice successfully teleported her original state to Bob. And now we also see why it's called teleportation, because Alice loses her original state. Because of the transformations we applied, it showed up on Bob's end. Alice's original qubit is in a different state. Therefore, we didn't violate the no cloning theorem. We didn't do cloning. We, so to say, teleported that state. And you see the caveat of this teleportation is that I also need a classical information channel. Alice communicated classically which of the measurement results she obtained, and therefore it's not pure quantum teleportation. So we teleported one quantum state by using classical, a classical information channel. All right, that's teleportation. There's some more information about quantum teleportation in my slides, specifically as to how you construct the quantum circuit as a circuit diagram. The last thing for today we're going to look at is Deutsch's algorithm. And per se, I wouldn't even call that one an algorithm since it only works on 2 qubits. So it's a generalization of an algorithm that's known as the Deutsch-Josa algorithm, which acts on a number of n qubits. In Deutsch's problem, how you want to think about it is that we're given a black box which computes a simple function, so an oracle, a unitary transformation. And the goal is to learn something about the possible function being computed by feeding in some input. So this algorithm, in this most general form, it only acts on 2 qubits, okay? So that means we're limited to 4 possible inputs in that case, which are 0, 0, 0, 1, 1, 0, 1, 1, as a lot of times when we talk about these simple algorithms. Okay, so any time we feed in an input, we say we're querying that black box. That's what it is. And the goal of this algorithm per se is to distinguish the first of these functions from the second of these 2 functions, So in other words, we have this black box, and this implements one of the possible functions. But by only feeding in one input, we want to find out if this function that we're looking at, that our quantum circuit implements, is in the first set of these 4 functions or in the second set of these 4 functions. And so let's create 2 sets for that. Let's say the set 1 is function 1 and function 2. And then we have the set 2, which is function 3 and function 4. And our possible inputs are 0, 0, 0, 1, 1, 0, 1, 1. These are our possible inputs. All right. And so let's see at the 4, or let's look at the 4 possible functions that we have. We have our first function that is given by function 1, gives as a result x, y. Okay, we have 2 inputs, x and y, and our function, given the inputs x and y, produces x and y. Then we have a function 2, which also takes x and y, but the output it produces is x, not y. Then we have function 3, which is x and x, XOR y, or addition modulo 2 y, and our function 4 gives us x addition modulo 2 not y. Okay, so this is what we're working with. And our quantum circuit that we look at implements one of these 4 functions, but we don't know which one. And what we want to find out is if the function belongs to the set 1 or to the set 2. And when you have a classical computer, you would have to do that twice. You have to do 2 calls to your oracle. Because for 2 possible input, 2 of these functions will give you the same output. Let's look at an example. Let's look at f1, 0, 0. So we look at that, the result will be 0, 0. Then we look at function 2, given 0, 0. Function 2 has x not y, gives me 0, 1. Function 3 of 0, 0 gives us 0, and 0 plus 0 is 0 divided 2, 0 is a 0 remainder. I need to switch that pen. That one's empty. And then we want to look at function 4, given inputs 0, 0, and the result for that one will be 0, 1, because we have x is 0, addition not y is x plus 1, so 0 plus 1 gives me 1, divided by 2 is 1 remainder, therefore I have 0, 1 as an output. And you see, this one and this one gives me the same output, and this one gives me the same output. So therefore, I would have to feed in another input to find out to which set of function my original function belongs to. Not so with quantum computing. Here we have an advantage, and let's look at that. So the first thing we want to do is implement our functions as unitaries. And you remember how to do that. We can always start with our single qubit operations, or our single, let's say I start with the bracket notation. Let's look at the first function here. Actually, the first one is pretty easy because it always gives me the same. So let's call it U1. And therefore, since the input always equals the output, it is the identity transformation. I'll look at function 2, which we implement as unitary 2, which is x not y. So I want to look at that. If you start in the bracket notation, you remember, you start with the initial state. Let's say it's 0, 0. And the result of that would be x remains the same, 0, but not y means 1. So therefore, 0, 1. We implement that as a matrix. So you remember the state 0, 1 in ket notation. In that case is 0, 1, 0, 0. And here I have 0, 0. If you multiply that out, you do 0 times 1 times 0, 0, 0, gives you 0, 0, 0, 0 for the first one. 1 times 1, 0, 0, 0 for the last one. Here another 4 zeros. Here another 4 zeros. Right? And then you would do that for all of the possible inputs. So here in that case, if we start with 1, 0, the result would be 1, 1. And again, in that case, 1, 1 is given by 0, 0, 0, 1, and my 1, 0 is given by, okay, so do that multiplication again, 0 for the first row, zeros for the second row, zeros for the third row, all zeros except the third one for the fourth one. You add these up, okay? And that you would do for all possible inputs. I will not do that here. You may give that a try and reproduce that for all 4 possible functions, for all 4 possible unitaries. I will just write it down in that case. We have 1, 0, 0, 0 here. Okay, for U2. Then we will look at U3. So U3 is given by that transformation. And the last one, U4, is given by that transformation. So these are our 4 unitaries that we have to our avail. And we want to implement that as a circuit as follows. So the whole circuit. So let's again start with an example. And the example in our case is a state 0 for the first qubit and the state 1 for the second qubit as an input. We apply a Hadamard transformation to the first one. We apply a Hadamard transformation also to the second one. Then here we have our unitary. So this is U of F1, U of F2, 3, 4. So it's one of these 4s that we find here, but again, we don't know which one. Then we do here is apply another Hadamard also here, and then we measure the system, okay? So, and measuring, again, depends on how you write your measurement gates, happens here. And then, if we do that right, then we learn to which set our function, so this unknown unitary that we see here, belongs to. How does that work? Well, let's just give it a try. So remember how the Hadamard transformation works. We just had it in our last lecture. This is the Hadamard transformation, the single qubit Hadamard transformation. And so if we apply it to this state and this state, let me just do it. We don't need to go through that calculation again, but if we apply it to the first one, then the result will be zero plus 1, and we apply it to the second one, which gives us 0 minus 1. Then we multiply that out. Gives us that state, okay? So depending on which unitary we apply now to that state, we will get a different result. And I need a little more space for that. So just remember these 4 unitaries here. I will quickly remove that. We don't need that anymore. So, and now let's apply the unitary 1 to that state, which we call psi. gives us, as a result, this state. So if we apply it to the second, if we apply the second one, you may give that a try. The result is slightly different. So the only thing that you see is a change of phases here. Let's remove that one here. Then we want to apply the third transformation, which leaves us with and then we want to apply the fourth one. And end with this state here. Okay, so then remember that we have still two Hadamard transformations left. So we are now, remember if we had our quantum state, we have our transformation U of F that we applied, and still we have these two to apply before we do the measurement. Okay, and now we operate on two qubit states. So what we're doing is, if we revert back to matrix notation, then the thing we want to do is take two single qubit Hadamard transformations and just write them down as a two qubit operation, which and lastly looks like that. Okay, and if we apply that transformation to whatever our state is, so depending on which transformation we see implemented here, we will get a different result. So this transformation applied to our state for the first one, let's say for U1 of psi, we get the result 0, 1. For U2 of psi, we get the result 0, 1. For U3 of psi, we get the result 1, 1. And lastly, for U4 of psi, we get the result -1, 1. What you see here is a global phase. So this is not a relative phase like the one that we see here or here. This is a global phase. And remember, global phases don't matter to the quantum state. It's still the same state. So therefore, what you see, if either U1 or U2, which gave us the same result before, are applied to my quantum state, then the result when measuring the system will be 0, 1. Otherwise, it will be 1, 1. So therefore, by only sending one possible set of inputs, in our case, we send 0, 1, I can distinguish between these two sets of functions. Okay? Set 1, set 2. So therefore, I know to which set of these functions my input belongs to, or to which set of functions the function that is implemented in my quantum circuit belongs to. So in 1985, when Deutsch discovered this algorithm, he wrote a very prophetic sentence at the end of his paper, which I put in my lecture slides. So you may want to read that. All right, that's it for today. The next time we will have a look at searching problems, and then we go from there. Thanks for your interest, and have a good day.